Hello, everybody. This is the second part of local astronomy, the PowerPoint for it. So let's just jump right in. We're going to start talking with the moon's effect on the Earth. And the moon is such a large object that in astronomy, we very often would think of the moon and the Earth as a double planet. They're so big in comparison to each other. Most of the other planets that have moons, the moons are very tiny in comparison to the planet. So our moon is kind of a special case, and we have a very special moon. So let's start off with the phases of the moon. Right? Well, the phases of the moon are caused by the Earth's, or rather the moon's revolution around the Earth. The moon is going around the Earth, and that would cause the phases of the moon. A lot of times it's initially a little hard to understand why the moon has the phases it has. Once you come to understand that, though, anytime you look at the moon, you have right away in your head, you know where the sun is, because the lit part of the moon, that half of the moon sphere that is lit, is being lit by the sun. So when you get that in your head, right away you start seeing the Earth, Moon, Sun in 3 dimensions. That's a useful thing. So half of the moon is always lit, right? Half of the moon is always in sunshine. It's sitting there in space. It's near the sun. Might be going around the Earth, but it's near the sun, so it's lit like the Earth is by the sun. Half of the Earth is always lit. Half of the moon is always lit. When we see the dark part of the moon, we'd call that the new moon. Now, if half the moon is lit, and we're seeing the dark side of the moon, where is the moon in relation to the Earth and the sun? Well, if you think about it, the Earth has to be on the far side of the moon. So the moon is between the Earth and the sun. So the moon, the half of the moon that's lit up is on the far side of us, is on the sun side of us. So the new moon would be in the same part of the sky as the sun is. And in fact, whenever we have a solar eclipse, it's because the moon happens to be crossing right in front of the sun. And so the solar eclipse would only happen on the new moon. That's when it just accidentally lines up with the sun. And one of the real interesting accidents in space is that the angular diameter of the moon, how big it looks, is almost identical to the angular diameter of the sun. Now that is pure accident, but that's really cool because it means we see spectacular solar eclipses. Now when we see only the light part of the moon, well, where would the moon be there if we're seeing the entire lit half of the moon? Well, that means that the moon has to be on the far side of the Earth. So the Earth is between the sun and the moon. And when we look back at the moon, we're seeing its full side. Now think about it for a second. If you're standing on the moon at the same time the Earth is seeing it as a full moon, and you're looking back at the Earth, what phase would the Earth be in? Because in fact the Earth goes through phases as well. So if you think about that, when we see the full moon, the moon, anybody standing on the moon would look back at us and see the new Earth, would see the dark side of the Earth. Pretty cool. So as we look at this diagram, on the right side we see the sunlight coming in, and we see that that's lighting up half the moon all the time. You also see half the Earth is lit up. What we see from the Earth, to understand that diagram, you have to stand on the Earth. So if you stand on the Earth and you look to the right, you see the new moon. In the second phase, the waxing crescent, when you look at the moon, you'd see on the right side of the moon just a thin sliver being lit up. In the third section, the first quarter, when you're standing on the Earth and you look at the moon, you see the right side of the moon lit up. Then the fourth section, you see more than just a quarter or more than just half of the moon lit up. That's a waxing gibbous. Waxing means it's increasing. Waning means it's decreasing. So the waxing gibbous is getting bigger and bigger until at the fifth section, we see the full moon. Now it gets a little bit more difficult because from the diagram's perspective, at location 6, I see the right side of the moon lit up. But stand on the Earth. When you stand on the Earth and you take that viewpoint and you're looking there, you see, it's the left side of the moon that is lit up from the Earth perspective. So in location 7, which side of the, did I say that wrong? The left side of the moon is lit up. In location 7, when you look from the Earth to the moon, which side of the moon is lit up? All right, so I'm looking and I see, yeah, it's the entire half of the moon that's on the left side. So you can't just stand back from the diagram and look at it. You have to get into the diagram. You have to put yourself from the Earth location and look there. And surely enough, on location 8, it's the left side of the moon that is getting thinner and thinner. And let me take my... So in location 8, you could see, sure enough, the left side of the moon. So everything that happens to the moon, okay, seems to go across the moon, one step after another. So here's another. All right, so take a look at that diagram there. Okay, and you get a better sense of how things work there. So in the waxing crescent, right, the light starts on the right side and sweeps across the moon until you have the full moon. And then as the full moon starts having nibbles taken out of it, that also starts on the right side of the moon and sweeps across the moon that way until there's not much left. And then we're back to the new moon. So why doesn't it eclipse every month? I can kind of show that to you here. All right. So if I have the Earth here, and this little thing is the moon, when they're going around each other, if the moon always is in the same exact plane as the Earth and the sun, sure enough, there will be eclipses every month. But the moon is not. The moon is slightly inclined, so it dips down below that plane, and then it dips up above that plane, down below. So as we're going around, the moon stays in that inclination. Makes you realize whenever we have a solar eclipse, 2 weeks later, we're going to have a lunar eclipse, and vice versa. So once the Earth and moon are in the right spot, so the moon is crossing through that plane just at the right moment, when it's either the new moon or the full moon, when it's crossing through that plane, 2 weeks later, it'll be crossing through that plane, coming back up or headed down. So it'll stay in that plane. So eclipses of the moon. The Earth casts a shadow in the direction opposite from the sun. As the moon moves around the Earth, it may pass through that shadow. When it does, it is called an eclipse of the moon. And if you think about it, as the Earth turns, more than half the population of the Earth will usually get to see a lunar eclipse, weather permitting. So in your lifetime, you've probably at least had the opportunity to see quite a few lunar eclipses, and you will continue to get to. Solar eclipses, though, the moon casts a tiny shadow, and that tiny shadow is only going to hit a small part of the Earth. And with the Earth's rotation, that shadow will draw a line on the Earth. Only people in that line will see a solar eclipse. We'll see the moon blot out the sun. People in a wider line will see a partial solar eclipse. You'll see a bite taken out of the sun. These are really cool things to see. Of course, you can't look at the sun directly without it potentially hurting your eyes severely. So you have to have methods to project. But during the last solar eclipse, when we were having, at least around here, a good part of the sun cut out, if you look on the forest floor where little bits of sunshine are coming through, you see little crescents all over the place. It doesn't take much to project it, and you get to see that. So why not eclipse every month? And that's just the moon's orbit is tilted. It's about 5-degree tilt. So the moon is usually passing above or below Earth's shadow. This is a great picture. Look at that. Though in those 3 images, you see the moon entering into the Earth's shadow. You see the moon fully in the Earth's shadow. Then you see the moon coming out of the Earth's shadow. But in those 3 images, you could see that circle that defines the Earth's shadow. One of the things I like to realize is that that's my shadow. Me and the Earth, we're the same thing, right? You don't look at the Earth and say there's little peoples on it. The Earth and the people, that's the same thing. So that's my shadow. That's your shadow in space. We cast a shadow in space. Usually we have no idea of it until the moon passes through it. Then you get to see that. So that's a lunar eclipse. Realize, though, that the moon isn't dark when it goes into it. Now, why isn't it dark? It's not getting any light directly from the sun. But if you stand on the moon and look back at the Earth has a very thin but substantial atmosphere. And if you were to look back at the Earth, when the Earth is eclipsing the sun, you would see the reddish sunset. You'd see a ring of sunset all around the Earth. And then when you are standing on the moon and you look around you, you would see this red light all around you. And sure enough, on Earth, when we're looking at the moon and it's in full eclipse, we see it as red. It varies quite a bit depending on the opacity of the atmosphere. If there's been some like volcanic eruptions lately, the Earth's atmosphere is a little bit thicker and a little bit more opaque to light, and it'll get a really dull, deep blood red. So, like, you get to see some pretty cool stuff with that. Nobody's ever quite sure how red it will be. But to see the full moon go into eclipse, and then to see the full moon as a dull, blood red object there, boy, that gets you. Really worth getting out to see them. Well, what about eclipses of the sun? Well, like I said, the moon also casts a shadow. It's small compared with the Earth, and only falls on a small part of the Earth. When the shadow falls on an area, the area experiences a solar eclipse. The solar eclipse will also not occur every month because the Earth will pass above or below the moon's shadow. We have another solar eclipse, I believe in 2024, coming up. It'll pass through the Rochester area in New York. It'll be very local to us, and it'll be really worthwhile to see that. So look at that that solar eclipse there. The part where the moon completely blocks off the light is called the umbra, and it's the darkest part of the shadow. If you take your fist and you put it part way in front of the sun, well, you'll still get so much sunlight on your face that it's really not blocking that much. But because it's blocking some, you're in the other part called the penumbra. Once your fist is completely blocking that sun, well, now you don't have any sunlight at all falling on your face, and you're in the umbra part of your shadow. And every shadow has both an umbra and a penumbra. Because the sun is a large enough disk that sometimes things only block out part of it. Then you're having a little light blocked out, you're in the penumbra. But if all the light is blocked, you're in the umbra. How about that? And there is the moon getting right in the way and finally blocking that sun completely. Now, when the sun is blocked completely, you could see something there. You could see this white light coming from there that you normally couldn't see. That whitish stuff there is always there, but the sunlight is so bright you can't see it. All that whitish stuff there, that is the sun's outer atmosphere, the corona. And when people see that in the sky, that's a pretty mind-blowing thing because it is beautiful. You see all these interesting lines coming from it. The ancients would have seen a solar eclipse once every couple generations. Your grandfather might remember seeing a solar eclipse, and he might say things like he saw angels dancing across it, or something that was mind-blowing. And because it was seen so very rarely, you just had the mythological stories about it. Now we get to see them a couple times a year. People go and take pictures of what it looks like, and you can see it is stunningly beautiful. This is a great picture. It's from the International Space Station looking down at the Earth. You can see a big dark spot on the Earth, and sure enough, that is the solar eclipse. That is the moon's shadow, the umbra part of the moon's shadow hitting the Earth. And you can see around it, it's a little bit darker than usual. That would be the penumbra. Penumbras are not that impressive to look at. It's just a little bit of darkening. But the umbra, certainly, yeah, you could tell under there, it is dark under there. The world changes. It gets cold. All the night sounds of the birds and everything start up. It really confuses all the animals. They're not used to anything like that. And then the light comes back. So, well worth getting to see something like that. So, apparent diameter. Well, take a look at this. Here's my fist. Whoa, look at that. That got a lot bigger. Did my fist actually grow? No. What happened? Well, it clearly got closer to you. So, if it's getting closer to you, that is only because, or you could tell that because it seems to grow in size. So the apparent diameter of celestial objects has a lot to do with how far away it is. So if an object gets closer, it seems to become larger. If it gets further, it seems to be smaller. This change is not in the object's actual size, but rather in its angular diameter. All right? So angular diameter is the angle the sides of the object make with the eye. So the angular diameter lets you know how much distance between objects changes over time. So the apparent diameter of the moon changes more than the apparent diameter of the sun. Sometimes we have solar eclipses where the moon fits inside the disk of the sun, and you can still see a ring of sunlight around it called an annular eclipse. Really cool. And sometimes the moon completely blocks out the sun. So you can tell that means the moon is getting a little bit closer, a little bit farther, a little bit closer. The sun really does not seem to change very much, which means our orbit around the sun is quite nearly circular. Very funny. People who say, who try to come up with the idea of how come we have summer and winter, and they say in summertime we're close to the sun, and wintertime we're far from the sun. Do you ever see the size, the disk of the sun change in angular diameter? I never have. I don't imagine anybody would ever notice. It changes a little bit, but not that you would ever notice. So that means our orbit is quite nearly circular. Okay, so the apparent diameter of the moon changes significantly more than the apparent diameter of the sun. So, like I'm saying, there's greater variation in the Earth, in the moon-Earth distance than in the Earth-Sun distance. This means that the orbit of the moon around the Earth is more elliptical than the orbit of the Earth around the sun. We're going to be talking about elliptical orbits. An ellipse is sort of like a circle that somebody sat on and got it squished. So we have to learn about elliptical orbits, and there's some simple mathematics that we have to talk about that. All right. One of the really neat effects of all of this is the tides. Right? So we want to try to understand this because the tides are a little bit more complicated than you'd think, but it explains some pretty big mysteries of the tides. So check it out. Both the moon and the sun pull on the Earth. The sun, is much larger, but the moon is much closer, and so the moon exerts a stronger pull. A bulge of water will always face the moon as the Earth turns. That's easy to understand. The moon, the water is able to be pulled more, and it's closer, so it's actually pulled a little bit. If you think about the Earth not being a single thing, but being a bunch of things moving through space, the moon is closer to the water part there, so it pulls it a little bit that way. The Earth is continuing in a little bit more of a straight line. The water on the other side is continuing in an even more straight line. So the Earth is pulled out from underneath it. And that's a good way to think about how come there's two bulges. One bulge is pulled more towards the moon. The other bulge is, well, it's what's left over after the Earth is also pulled a little bit more towards the moon. And so you end up having two bulges, one on each side of the Earth, and they're equal-sized bulges. So the Earth turns once a day underneath these two bulges. That's two high tides. Now let's extend our thinking a tiny bit more. If there's two bulges and the Earth has to turn through those bulges, the land of the Earth is going to run into those bulges. Do you suppose that's going to slow the Earth down? Yup, it slows the Earth down. But is the Earth going to pull a tide on the moon? Of course, the Earth is going to pull a tide on the moon too. And the moon having to rotate through that tide, now it's a land tide. There's no water there, so it's actually a bulge of land that's lifted up about a foot higher than normal. And the moon has to rotate through it. That's hard to do. And it eventually stopped the moon turning. The moon used to turn, so we would see all the different sides of the moon. Have you ever seen the back of the moon? Me neither, and you never will, unless you go into space. The Earth has such a strong influence on the moon. Even though the moon used to turn, it doesn't turn. It always keeps the same side facing Earth, and that's exactly because of tides. That's not a coincidence. There's no coincidence there. That's a tidal effect. The Earth stopped the moon from turning, but the moon has slowed the Earth's turn down. So these things are all tied together. So the sun also exerts an influence. So therefore, when the sun and moon are pulling from the same direction or exactly opposite direction, the tides are larger than usual. These are called spring tides. Okay? So if the sun and moon are both in the same spot in the sky, now what kind of phase of the moon would that be? Give you a second. If the sun is there and the moon is between the sun and the earth, that would be a new moon. So both tides that are caused there are big tides getting pulled in the same direction. That would be what we call a spring tide. But because there's a bulge on each side, if you have the sun, earth, and the moon is on the exact opposite side, that's also going to do the same thing. So we get 2 spring tides a month, at the new moon and the full moon. When the sun and the moon are at right angles to each other, they're trying to pull a tide all over the earth. Doesn't work very well. So none of the tides are nearly as large as usual. We call that a neap tide. So what phases of the moon would cause neap tides? First quarter and third quarter would be neap tides. So full moon and new moon would cause spring tides. And if you're down by the ocean, you really will notice this. The tide comes in, and it's a bigger than usual tide. We always worry about that when a storm is coming ashore, and you have a full moon or a new moon. Oh, that storm is going to bring in a storm surge. And if that storm surge hits right at high tide, and it's a bigger than usual high tide, that's a problem. If it happens during first quarter or third quarter and the storm is hitting there, it's not as big a problem. So these things are tied in all over the place. So take a look at the spring tide. You see what I'm talking about? The sun and the moon are both pulling the bulge in the same place. How cool is that? So you get a big tide there. And if the moon is at right angles, in the second part of the diagram, moon is at right angles, they're trying to pull a bulge all over the planet Earth, so you distribute the water better, you don't get nearly as high a tide. So all of this is due to gravity. So we need to think about gravity a little bit. So gravity is just all matter pulls on all other matter. Gravity's weird. The atoms in your body are pulling on the atoms in the Andromeda galaxy, our next nearest galaxy. As a matter of fact, the atoms in your body are pulling on all other atoms in the universe. That's, if you think about it, a little crazy. Like every atom in the Andromeda galaxy is pulling on you and you're pulling on it. All right? Anyway, that's gravity. And obviously you're standing on the surface of the Earth. Next time you're outside, drop a rock and just realize that the amount of matter that you have to be standing on that's under your feet is huge for it to pull the rock down so hard like that. It's a lot of matter. So the Earth holds everything tight to it, and that's with a force called gravity. So the strength of gravitational attraction depends on mass. Well, whose mass? If we double the mass of the Earth, it will double the gravity that the Earth is pulling you with. What if you were to double your mass? Not recommended. But what if you double your mass? If you were to double your mass, you have twice the force of gravity pulling you down. You'll notice a scale when you stand on it indicates that you've doubled your weight, right? So if you double the Earth's mass, that spring scale that you're checking your weight, that would double. What if you doubled your mass and the Earth's mass? Well, 2 times 2. The scale that you're standing on would be 4 times as great. So the farther from an object, the weaker its gravity. When you are an astronaut and you fly up above the Earth's surface, yes, the Earth has less gravity on you. That is not why somebody flying around in the International Space Station appears weightless, because they're not so far from the Earth. The gravity is almost the same as the Earth. There's a whole different reason with that. They're going in orbit around the Earth, and they're falling all the time towards the Earth. But they're going forward at 5 miles a second. That's the magic speed. At 5 miles a second, as much as you're falling towards the Earth's surface is falling away from you. So you're actually falling all the time. So if you were in a room and you were lifted 10,000 feet in the air and then dropped, you would seem completely weightless, compared to the objects in the room. Now you're not. You all have the same gravity. It's just you're all accelerating towards the ground at exactly the same rate. You're falling towards the Earth just like you are in the International Space Station. In this case, however, because you don't have that forward motion, it's not going to end as well. So weight is a force caused by gravity between two masses. If you moved away from the Earth, notice your mass would remain constant, but your weight would decrease if you moved away from the Earth. Now, the farther you get away from Earth, the more your weight would actually decrease. If you go out to the orbit of Pluto, the Earth is still pulling on you, but so little that you wouldn't really notice it. I mean, after all, the other planets are pulling on us as well. That's the only effect the other planets have on us. They're pulling on us. But the Earth is so much closer that it pulls on us so much more. Let's talk for a second about orbits. Any object in orbit around another is said to be a satellite of the object. The Earth is a satellite of the sun. All the planets are satellites of the sun. The moon is a satellite of the Earth. All orbits, every orbit that happens is actually an ellipse, with the sun or whatever object is being orbited at the focus point or foci of the ellipse. Okay? As a planet orbits the sun, when is it going to move fastest? Well, if you fall off a building, don't do this. How about if you dive off a bridge to the water below? When are you moving fastest? You start slow and you go faster, 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 and just before you hit, you're moving the fastest. All right, so if a planet is in orbit around the sun, when is it going to be moving fastest? Well, it's falling towards the sun, so as it rounds the sun, when it's closer to the sun, that's exactly when it's moving fastest. As it pulls away from the sun and goes out to the farthest part, sun is slowing it down as it goes away from it. So like when you're on a trampoline, you're fastest when you hit the trampoline. When you come up, you're slowest as you're getting to the high point, because Earth's gravity is pulling you down. So even though you're going up, you're being slowed by Earth's gravity. And then you start falling. And as you start falling, you start going faster and faster. If you're moving in direction that the gravity is pulling you, you're going faster. If you're moving opposite that direction, you're going slower. It's kind of simple stuff. So one of Kepler's laws was a brilliant one, and that's that planets sweep out equal areas in equal times. So if you're, well, I think I have a page on that. Let's just talk about the energies. So we have two words here, perihelion. Helion means sun. Peri means closest to. Aphelion means farthest from. So you can think of ap and away. So aphelion is when you're furthest away. Perihelion is when you're closest. And we want you to know about the orbital speeds. When are we moving fastest? Perihelion is when you are booking. You are moving really fast. And as you get further away, your energy decreases, your kinetic energy decreases, your potential energy increases. So you always have the same amount of energy, it's just changing between potential and kinetic. Again, sort of like being on a trampoline. When you're high up, you have a lot of potential energy, and as you're falling down, you convert that potential energy to kinetic energy. You start moving faster and faster. As soon as you hit, you're at maximum kinetic energy, and then you start going up. Some of your kinetic energy starts changing back to potential energy. If you think about a pendulum bob on a clock, same thing. When the bob is up here, it's moving very slow. Kinetic energy is 0. Potential energy is really high. When it's right down here, potential energy is 0. Kinetic energy is maximum. So next time you watch a pendulum clock go like that, be absolutely fascinating, because you're seeing energy transformations. You can sit there all day and watch that. It's awesome. Here's that equal areas law. Check that out. If this is the Earth going around the sun, and that doesn't work because we don't change, that's highly exaggerated for the distance we change, but the diagram makes sense. When we look at if each of those are a month, when we're at aphelion, we're making a thin pie slice, but it's long sides. When we're at perihelion, we're making a short pie slice, but we're moving very fast, so it's a big fat piece of pie. Both of those areas, if they're swept out in, say, 30-day periods, both of those areas are exactly alike. Mathematically, that's one of those kickers. That's pretty cool. But the upshot is it just means we're going fast when we're close to the sun. We're going slow when we're far from the sun. Got it? When we do our orbits drawing, and we have to get you good at doing orbits drawing and measuring and doing calculation. It's not very hard, but it's kind of cool. Look at the variables here. All orbits you define by this ellipse with two foci. Now I'm going to do some drawings on it. I'll make another video that I'll post for you where I'm doing the orbit drawing. The sun is at one focus. There's nothing at the other focus. It's just a mathematical point. How would you determine where the other focus is? Well, look how far the sun is from the side of the orbit going around it. The other focus would be just as far in from the other side. So that's easy to figure out. So the distance between the two focal points we would give as little d. The total length of the major axis. Now, why do we call it the major axis? Well, you could draw two axes across that elliptical orbit. One would be the longest line you could fit into that elliptical orbit. The other would be the shortest line you could fit into the elliptical orbit. What would you name those? Well, how about the shortest axis you'd call the minor axis. The longest axis would be the major axis. So capital L is defined as the major axis. The only things you need to know about are the distance between the focal points and the length of the major axis. And you can see with a ruler, very, very simple things to measure. Okay, and we'll put those in a calculation for you. I was talking about the annular eclipse. Take a look at that. That is gorgeous, isn't it? The moon fits right inside the sun. That's because the moon's distance varies enough, so sometimes it'll do that, sometimes it'll do a full solar eclipse. That's that full solar eclipse, and if you get a chance in your lifetime, you should see that because it will blow your mind.